Hello, this is Jonathan Templin, and this is a lecture on repeated measures analyses. Repeated measures ANOVA, multivariate ANOVA, and how these two classical versions of multivariate statistics relate to what we've learned in the course about linear mixed models. This is EPSY, Fundamentals of Multivariate Modeling. So to talk about repeated measures versions of linear models, so how repeated measure models work, and how they are actually mixed models with some very strict assumptions. We're also going to expand them a little bit and talk about multivariate and how it well, and see how that is also part of the mixed family. I'm mentioning this to you because oftentimes when I teach these types of modern versions of doing it, talk about this with your advisor or other colleagues, they might say, well, what about doing a Manova or repeated measures ANOVA? And the answer to that is, I already am. In fact, I'm doing one that's better because the mixed model versions of give you better data and better protection, better versions of assumptions that you could make about the resistance variances. So at the end of all that, we're going to also have an introduction to level models. This is a hierarchical linear model, other ways of looking at it, that might have some type of structure. I'm mentioning that in this lecture because, again, very one further extension from the models that were today. For today, and to make this comparison, you must assume that you have complete, meaning there are no missing observations, there are no missing features. Without that assumption, the start to break down, and that's that is because of the way the software treats the missing data. In the classical versions, you have one piece of data missing, the whole case is all the where in the modern versions, a piece of data missing may not throw out the whole thing. It depends on the piece of data it happens to be. So our example data today are an R, an of participants examining impact habits and exercise on pulse rate. So we have 18 people, and we collected 3 pulse rates after jogging and after running. So these are the 3 outcomes, 3 dependent variables. You can imagine that these pulse rates are all the same, essentially the same scale, number of beats per minute. Then we took the subject and we found that there were 2. We put them into 2 different types of 3 different types of so they types of classes of whether they were either in an aerobic stair class, racquetball, or weight training. One of those 3. They were randomly with so to each 3, and then we had a diet factor where we had a couple of 9 vegetarians and 9 non-vegetarians. I put them as omnivores, eat meat, and I assume they also eat vegetables as well. So let's get into repeated measures ANOVA. Measures ANOVA. Instead of focusing on a variable, we're going to focus on all 3 at once, right? So up to this point, if we had to like a linear model, we'd have one outcome, and we would like that pulse rate, let's say, up or something along those lines. The repeated measure analysis allows us to look at all 3 simultaneously. So in repeated measures linear models or general linear models, the effects of interest that we're after are whether or not we have between subjects effects, right? Differences between diet and exercise type effectively. We could also look at whether or not we have subjects effects, right? So difference for when the pulse rate was. This is often not a consideration when we do multivariate. Also could be there as well. And we might find or look for an interaction between when the pulse rate was taken and either diet or exercise or both. And as we're going to see, the repeated measures general integral uses multivariate data and has multivariate distribution. In particular, when we have measured a person, just like we did with our multivariate regression or our path analysis, for observation I, you would have a set of, if we wanted to do that with multivariate outcomes, again, this would follow distribution Y condition predictor, this multivariate distribution, where the mean vector would be given by the predictor times matrix of fixed beta, and you'd have some type of residual covariance matrix V. And in at least squares estimates, now we would have this large, or this estimate for how we get our beta. And back this a little bit more. The distributional assumptions that we have measured are very similar to what we have in our mixed model. Again, the for the means provides our predicted values for each obstacle. For the variances now has in the diagonal elements the residual or error variance for each outcome, and in the covariance error between pairs of outcomes. So this is what we saw when we started doing our multivariate regression. We could go and talk about how far for both outcomes simultaneously. This is what happens with this variance covariance matrix. So the key to multivariate is that matrix. This is the thing that differentiates repeated measures from multivariate ANOVA model itself. And in particular, repeated measures ANOVA puts a very strict assumption he can look like, whereas multivariate tries to estimate thing in V. And depending on and depending on the types of analyses you want to do, you'll find that these are either overly strict or overly lax, and that's why we'd want to use more of the modern approaches to analysis, the mixed model. But again, this lecture is to show you how we used to do things, so if anyone wants to talk about your analyses, I'm doing that only better. So here are the three types of structure, the V matrix, in our classical general linear model. We could start off by thinking that we had independence and observations. In this case, it's like saying the V matrix would be diagonal, the identity matrix, so a square matrix with a diagonal of 1. We multiply by a common residual variance, and what that appears to be that every observation has the same residual variance, and that all residual terms are in each other. Basically, what we would get out of doing separate analyses from a general linear model. However, one catch in separate analysis probably have different for each dependent variable. Measures, however, assume something called the observation. Sphericity is a crazy word, and it's a strict assumption. But what it boils down to, a little bit more strictly, is something that we call compound symmetry of the V matrix, or of this residual covariance matrix. What that is that the diagonal elements of the V matrix are all equal to each other. That means the same residual variance. Now, this is hard to believe in many cases. We're going to see this in our data. That would be like that we predict our outcomes. The variance of that is regardless of whether we had a pulse rate or a pulse rate after exercise or after running. So with that, the reason why I have a hard time believing that is that two pulse different amounts of variability in that, because when you're sort of at warm-up, when people are close to resting, their pulse rate's a little bit lower, they tend to be more homogeneous. Variances are a little bit smaller. However, there's wide differences in pulse rate after physical activity because of the differences in genetics and conditioning. So what you'll see is when we go and test people after running, we'll have high amounts of variation in how much their pulse rate is. Now, if you map that onto this repeated measure analysis, the assumption, though, is that the variance after we predict it is all the same. Or it goes a step further, they're all correlated or covariant, same covariance as well. It is really a difficult assumption to believe, and if it isn't enacted, then we have some type of adjustment to the have to do. It's a hard that we get, and a lot of people still use structures of this assumption is. Now, the multivariate version, or Manova, multivariate model sense. It's nothing, and it estimates it, right? So it's going to estimate every single variance, every single covariance. And for it to work well, we need a larger sample. It's very hard to estimate all those. You'll see that today with 18 observations, 36 pieces of numbers, 18 observations times 3 time points. This is the most general procedure. So what we're going to want something usually somewhere in between these two. And the classic statistics that we would end up doing doesn't really work for us in this range. So if we go to a working example, we're going to start with the unconditional model. And I'm going to provide this as a baseline to talk about how repeated measures works. Now, you'll likely never. So to do this, I've converted from one where we had per row. So here's how the data look when you enter the NR. The data exercise is what it's called. When they come in, you see that each row is one person. We have their 3 pulse rates, we have their diet, and we have their ID number, and we have the exercise case that we were in. But then we go and reshape into this set like we had to use for the NLME and in our mixed model, where I now takes up, for each pulse takes up one row of the data. So there'll be 36 observations altogether. Pardon me, 54 observations altogether. Can't do math, pardon me. So that's where we start. We'll reshape this. And here's the data, you can see that. The empty model is one where we're just going to do linear model on dumb effectively the time variable to allow us to have different means come about. Now this analysis, when we do, time variable goes in as a dummy coded, as 2 dummy codes. What we end up getting here in the output, you can see right here, we have an estimate of the mean for each of these values. And furthermore, we have an estimate of the residual error or the residual variance of 7.66. Now, there's only one residual variance, and we're also treating all 3 observations as independent. And so it looks like quite a big sample size. In fact, it says 51 degrees of freedom. There's each person's rate at all 3 times is going to be correlated, and this is not adjusting it for it. So this is not analysis to do, but this gives us at least an idea as to what's coming out of the computer. And if we go and look at this, and actually let's go interpret the mean vector real quick. The intercept represents the mean at time 1. Time 1 is the reference group in our and so pulse rate after warming up. This beta weight for time 2 is not the pulse rate, the mean pulse rate at time 2. That is the difference between pulse rate at time 2 and pulse rate at time 1. In this case, 46 beats per minute at time 2. Once again, if I were to try to go and figure out what that time 2 would be, go back to the beginning, after jogging. So it's warm up is time 1, jogging is time 2, and running is time 3. Makes sense. You'd say that, and on average, the pulse of our sample goes up about 46 beats per minute after jogging compared to after warm up. And for time 3, this is now the difference between after running and the reference group. So we'd say it's 102 beats per minute faster after running. So we put this together. We see our beta vector. It's just this set of betas that we put in there. The residual covariance matrix is the diagonal. It's 507 points down the diagonal. That again came from the squared residual standard error of 22.53. So the repeated measures model does this a little bit differently. It changes the structure of the V matrix to what you see in this box here. So what is this? There is a common residual variance term. And the diagonal consists of that common residual variance term plus some parameter tau, which also be the covariance. So that is this idea of compound symmetry. When you look at the covariance matrix, you can see it's compound symmetric if the diagonal values are all the same and the off-diagonal values are all the same, even though the off-diagonal may be different and is likely different from the diagonal itself. So to do this, we use, in a classical sense, we could use AOV go too deep into this. Really, I don't want to. I'm going to give you the keys to the car, use the classical. You can do this in a mixed model and be much better. So here is the output that we get. It's impossible to see what the covariance structure is. You don't even know what you're doing. You're just looking at, hey, I've got this time variable. It's got a p-value over here. I'm good. But really, what we need to do is compare two outputs. You can start to see a little bit of where things start. Right? And you can have an analysis of variance table. Over here, you can also take a look at values for our output here, and you'll look over here at our values for of 137.0556. Time 1 and time 2 have similar values. The 137 is an odd number. Why they put that there. Sure. But if we switch to the GLS function from the ANOVA package, we use likelihood, and we use the correlation, this core comp sim function, where we put in a one pipe ID telling us which ID to use. Now we get output that looks like what we saw previous to this. We see our values of each of our beta are the same, but estimated correlation between time points. Correlation between time points is the same observation. Us understand what we would expect to see when we go a little bit farther. All right, so ID, if we do our summary of our repeaters and the AOV function, you saw that our statistic was 635, and sure matches what we got from a repeated ANOVA empty model of 633.460. So moving forward, the GLS function has the get RCOV feature. And this allows us to look at the covariance matrix. And sure enough, here it is. Look at the diagonal. 507 down the diagonal. Off the 4.49 in each spot. That's compound symmetry. The diagonal is all the same. The off diagonal is all the same. The standard deviation is the square root of the diagonal here of 22.53. And sure enough, if you go back to our original analysis, you saw 22.53. This is independent model. This is LM. This is the first thing we did where we don't have any type of see. It has 22.3 for the residual error. So I'm trying to tell you with this. I understand. I'm like matrix this, blah blah blah. Don't need to catch that. Telling you when you do it both the same numbers. Getting the same numbers means we have the same method, whether we're doing it with the old way or the new way that's more flexible. So that's the point of this lecture. We're doing things. So again, we can this compound symmetric covariance. It looks like right here, right down the diagonal. 4.2 is really our resistance estimate, and 433.5 is our covariance estimate. The nice thing is that REML for us to test the covariance structure between. And as a matter of fact, we can go and take our and put the two models together and see if our model is preferred. Right? The only thing that's different between our model and is the covariances are all equal to 0. And we can test that and get a likelihood ratio test. Right here, see that sure enough, p-value is small, meaning that our model with covariance is preferred. And why it's preferred is, if we get back to our output here, that correlation we're estimating of 0.85, a long way from 0. It's telling us what we can predict itself. Yes, we want the measures a note compared to the plain one. So if we were to do the full analysis, we can put in our predictors now, and we can go and do things the way we need to do to see our results. We're going to get a between subjects effect. We're going to see main effect interaction in an exercise, for instance. We might see subject effects for main effects of when the pulse rate was. We might find this pulse rate and each of the diet and exercise factors themselves. Within subjects, can have adjustment to V. but we don't have that. We have any adjusted feature if we were to use the AOV classical sense. If you use SPSS and you'll end up getting a column of that say the p-value if the assumption doesn't fit. But the key with this is we don't need a ability to test the fit of the right to make sure that it works ahead of time. So that's what we're going to do. Here we have our model where we put all of our variables in. Exercise type, a factor, essentially levels, 2 degrees of freedom. So there's 3 levels of exercise type. Diet has 2. We have the exercise type and diet as well. We have a bunch of other terms. The error term, these are all the within subject factors, time. Again, the way of doing this. And with this, you can get a sense for our p-values. What does this tell us? Well, overall, let's get three-way interaction. No three-way interaction present. Looks like two-way interaction. Sorry, no two-way size, type, and diet. Time being pulse rate, which time. Two-way interaction between diet and time. So that would also be the case. Here it looks like the only thing that's significant is main effect of diet. So there's only a significant difference between the vegetarians and the non-vegetarians in their pulse. Now if we do the same analysis with the LME approach, what you should find is roughly the same numbers difference. Effective exercise is p-value of 4AA. Sure enough, that's real close to what we saw before. There's some rounding error that goes in with this as well. But nothing that would make us change our conclusions whatsoever. Again, main effect of diet shows up here. Previously, I forgot to mention there's this huge main effect of time, and we would expect that. Time is our pulse difference for the 3 exercise points. And we would expect to have a huge difference in exercise, regardless of which group we're in. And that's what we end up seeing. So we have the same results values if you go side by side. Key difference between the two is that LME provides a little p-value, and that's because LME or this GLS file is different when determining the degrees of freedom for the denominator. So this is already starting to do things that are a little bit different from what we saw. Again, just for the F, same. How do we go and approximate what we need to do to make our test accurate? I believe LME is a bit more accurate. More, we can take a look at this is our MPI model residual covariance matrix. Here's our the model where we put in our predictor. You can see how the residual variances shrink, the residual covariance shrink, and now we can look at the R squared. And again, because the variances are all the same, the R squared for each predicted variable or dependent variable will be the same of 0.239. There's a multivariate version. I don't like to talk about that. Now let's compare what we're doing with the classical Manova, where we can estimate everything models. With Manova, again, we can do everything all at once. Between Manova and repeated measures ANOVA, is the V matrix in Manova is fully estimated. We estimate variance, we estimate everything in there. Whereas in repeated measures, that has less of an influence. It has less, pardon me, the version of it has the same diagonal, just compound symmetric, same diagonal. So there's only 2 elements estimated in repeated measures, whereas in Manova we're estimating the whole thing. One of the differences in Manova versus repeated measures, particularly from a classical approach, is more often doesn't give you those within subject effects. They just happen to be different. So let's take what happens. The Manova estimates every single term. There's a different symbol for each spot in the V matrix. Compare that with repeated measure symmetry. Diagonal being the same, off diagonal in total numbers. Symmetry. So what are the key differences here? In Manova, we have more model parameters. I would say less parsimony. What we need, though. Has fewer assumptions, which is good. And it is better for you if repeated measure assumptions are violated in a class. But with our linear mixed effects models, we don't need this because we can fit a more version of the matrix to our data. In repeated measures, however, we have much more strict assumptions with more power multivariate if our assumptions are not met, but it also could lead to have some type 1 rating when our assumptions aren't met. The multivariate ANOVA has a different set of test statistics that you typically find if you were taking a classic version of this in statistics. The test statistics go by the names of Wilks lambda, or Pillai's trace, or Hotelling law, or Roy's root. All of those, your best named tests at all, but they are what they are. I'll have to use them. But what I want to tell you is we can recreate at least one of them, and actually more, with our mixed model as well. Just to show again that Manova is the same thing as a mixed model with the right structure for the V-matrix. How we define the score is through this complicated series of bands. I'll just skip ahead on that. Blah, blah. That's what my son thinks I say at work today. Here we go. This is it. Effectively get a lambda. And sure enough, we could actually go back to data now and just show you what we get from analysis. If we do a Manova with an empty model, there's a Manova function that's in the base R package. And here's what you get when you the output for it. T-sparse effects for each. Basically what it's doing is it's showing you for each dependent variable what the residual variances happen to be. For the mixed model version of it, we can put that in the GLS function, and now we can use the QM function again along weights, different variances and covariance. So this is estimating all the values that we see. Here we get a bunch of output. Now when we look at this output, let's go and take a look at the varcove function. Varcove function shows you that down the we have a different residual variance for each, and sure enough, time 3 has a big time 1 and time 2. It's what we expect based on the nature of physiology and exercise science. The off-diagonal have differing covariances as well. See, this analysis is giving us each of the values we want. If you also flip, so let me just flip ahead quick. Yeah, go back one slide. Take a look at where residuals for each of the Manova output. This is your hint that these are going to be the same. The residual variance of residual, which is an estimate of residual variance, it was 279.91 for the first time point, and that's identical to what this was doing for our model. Same thing goes the other two, 473.05, 473.05, 70.03, 770.03. So again, blah, 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 matrix, blah, 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 model. Wait, there are the, so I've been teaching repeated measures ANOVA in the mixed mold without even having to think about what these are. And here, sure enough, residual covariance matrix. Ta-da. If we want to go put every predictor in, this is what we do. In the classical approach, we would exercise and their interaction. Now, it doesn't look like it has the within subjects effect. This is very different. For each statement, we can ask for each test statistics. Wilks lambda applies Hotelling Lawley root and Roy's largest root, and it will give each of those values here on the any test. And we can do the same thing for our model. We can put all those in. Again, we have the correlation being core sim and the weights being var ident talked about. Again, we get our bunch of fixed effects here along with our p-value F statistics and our new variance matrix. And here we could actually do a combination to show differences between the two, although I don't example just because it's sort of inconsequential after we get a little bit further. But I'll show you this if you need to. So what are the benefits of using classical measures and Manova? Benefits models over classical repeated Manova. So here what we see is the sort of spectrum of model parameters here. I just try to put these on the same kind of a sliding scale. The very first model, the independence model, is over here. This is regular ANOVA. Has some very restrictive assumptions. Has very few parameters. Here for compound symmetry, we see our compound symmetric V matrix. Again, same to somewhere in between independence. Our last one, which is unstructured, which estimates every single variable. So this is the continuum you see between more parameters and much fewer assumptions to fewer parameters and much more restrictive assumptions. But the key is, there is, in the classical sense, and if we're doing this the ways that we used to teach you in other classes, you'd have no way of determining which V matrix was most appropriate for your data. Well, that's the nice thing. We can test to see which V matrix makes sense. So for instance, took the full repeated measure of the compound and compared it with the full model from ANOVA, and sure enough, I get the p-value of 0.0013. Now I rescale. This is not using the maximum, which is something that would be nice to have, but we don't have it now. So we end up getting a value that would basically, we would reject the repeated measures ANOVA model, and we would accept ANOVA here. But furthermore, could also come up with a new covariance structure altogether, right? So in the classic sense, all you got, this is your menu. Yeah, there you go. It's like going In-N-Out burger. Cheeseburger, hamburger, and double cheeseburger. So here is what you have. We could just come up with a brand new. So this is a new, where we're going to try something different. We're going to call this heterogeneous symmetry, meaning we're going to have different covariances. So the off-diagonal elements will be different, but we're going to make them have the same correlation. So how do we do? Right. So if we just change the var ident and the correlation slightly, what we're going to get, the covariance matrix looks like this, right, which looks like everything's estimated as a different number. However, and take a look at the correlation between the correlation matrix, see is the correlation, diagonal correlation of the residuals are all held to be equal, whereas the variances are allowed to be different. So what this is estimated is actually 4 parameters. There's a covariance parameter, or a common correlation parameter part, and then 3 variances. So this model actually, if we were to go put this on the menu, show up somewhere in between compound symmetry and unstructured, right over here. But go back to it and just take a look. If we were to put this in the ANOVA mix, all 3 out here, what we can tell is that the compound symmetry heterogeneous, the CHH model, is preferred to the repeated. That seems to be obvious because the diagonal elements are very different. However, when we with the Manova, you'll see the p-value being very small. It means it fits as well as our current model. However, Manova takes 2 more parameters to do so. So because of that, we're losing a little bit of power, and in an 18-person study, that's a big deal. In fact, if you were to go and look at the fixed texture, you might actually another done this in the past, see that some of the people actually flip direction because of the use of those two parameters that we want. So the bottom line from this part of the lecture is this. All the stuff you're learning in here doesn't by the same name that your advisor or some of your colleagues might call it. ANOVA and repeated measures. That being said, it is the same. It's not only the same, it's because we can also do more powerful tests to tell which model is most appropriate, or we could custom fit a model or more likely fits the data that we have, helping us with parameters, number of parameters estimated. So key is you've already learned repeated measure ANOVA, and you already learned Manova. So if someone wants you to do those, just say, I'm already doing that, or send me an email, and I'm happy to explain it for you. So let's move on a step further. One step forward from this would be the case where we want to add a coefficient. All right? What does that mean? Well, if you think about it, our measure has, or our mixed model, or any of these models where we have multivariate linear models, as I'm calling, we end up having multiple observations per person or unit in our analysis. In this case, we have pulse rates nested within person. With that, instead of using this where we try to play, we could instead build an approach where we add for each person now what we call a random intercept, this use that I have on this here. Is effectively, we've changed ever so slightly to say that each person, there might be individual differences in where their intercept might be, or pulse rate. But sure enough, when we add that and do that, we actually are doing the same type of analysis. We have repeated measures ANOVA in our analysis as well. The beginning point for our multi-level models. This is the stuff you'd see if you were to take a hierarchical class or longitudinal models class. About that a little bit. Our multivariate model here has a little bit more terminology to it. So right here, this line looks at our overall fixed mean. Let's call this our mean. But these blue and purple and boxes represent 3 different people from our study. And so here, these aren't really 20 beats per minute pulse, but you could imagine maybe a different number on the y-axis here. This person has very low pulse rates. This person blue has very high ones. The person yellow is right about average. If we were to go and take from each that blue dashed line, blue, yellow, and purple, that would be a person average right there. So whereas the intercept represents an overall average across all people, the average rate, each person's average is going to have a little bit of a deviation from that intercept, and that's given by these red arrows, double-headed arrows right here. And so what this is doing, allowing us to talk about variation or between people, right? Talk about the variance of how much people's intercepts vary, right? The dashed person's intercept might be. And then if we go inside of each person's little arrow here, there are 4 little arrows, and it depends on how much data we have for each person. We can have a different amount, okay. But here we have 4 cases up top. Has 2, the purple has 5. But how much there is on average within person characterized by within person variance, right? So this is sort of inter-individual differences. So how much do people differ in pulse rate versus individual differences? How much does pulse rate vary in a person across time? Now the analysis model, we build this, starts to look a little bit different. We start out with a general linear model right here. This is general linear, pardon me, this is what the general linear model has, fixed intercept, residual variance term. However, in the multi-level model, we end up having a placeholder, this sort of a notation scheme that has placeholders to show multi-level notation. So now each person's observation has 2 subscripts, a T and an I, time the person here. Sure enough, each coefficient that you see on the right hand of the equals of this, what we call level 1 model, has an I as well, indicating that each person gets an intercept and each person has their own version of it. But that person intercept is really a placeholder, and we can put this at what we call the level part of the model and model it with as a function of an overall grand mean. This would actually be a fixed intercept, and an individual error term with this, and this here, the random intercept per person. And this level 1, level 2 dichotomy helps us think about the types of variables we might put in our analysis. If we wanted to describe variation in person differences, we're going to have to put person level variables in the analysis. This would represent diet or your exercise type, because these were all assigned to a person. Now, level 1 variables, however, represent things that happen for each time point of the observation. So this might be where we put our the different types of exercise that made people do, running, jogging, or warming up. We can quantify what proportion, something called the intraclass correlation, which talks about the proportion of variance that is between persons, or the average correlation across observations as well. And now the V matrix that we've talked about up to this point actually gets put together through two different matrices, something called a G matrix, which is your variance covariance matrix of your random effects. In our case, we just have a random intercept. And an R matrix, which is now our matrix of residual terms, or residual matrix. This is where it ends up coming from, how it puts together. So why I'm saying this is if you were to go and take a multi-level class, you're actually well on your way to getting it, I hope, off the bat, rather than having to relearn what you've learned before. Let's talk a little bit of analysis advice. This is sort of model salad that I threw at you today, a model buffet. What happens? When should we use what? Well, you could use repeated measures if you have complete data, right? Nothing is missing. Perhaps you have a small sample size, and your data meet the idea of sphericity, which really is how we go and do compound symmetry. How do you know this last one? You don't. So it's sort of a problem. Multivariate ANOVA, if you have complete data, again, you have a large sample size, and your data don't meet sphericity. And again, how do you know the last one? You don't. Now, that said, I mean, methods could be useful. The problem is you can't choose which one you would prefer, the R matrix. So here's when you don't use these. Use a mixed model if you when you don't use these. If you have independent variables that you wish to see with each that vary with each dependent variable, right? We use multi-level for that. You've got missing data. Ooh, that's tough. Actually, I'm going to use this to show you what we're going to do with multiple imputation in a later lecture. If you have categorical data, you can't do this. If you have data that come from psychometric measures, that's where you'd use a structural equation model. Or if you'd like to determine which type of V or R matrix you have. So pretty much, yes, you could use these models or these methods, but you certainly have no way of understanding whether or not you're doing things correctly because they're sort of they're very limited in what they can tell you. So to summarize, repeated measures ANOVA, multivariate ANOVA are the same as mixed models when we go and trick out our mixed models to look like them. However, mixed models do much more. They help you with missing data, they help you understand which model seems to fit the data best, and they help you design a model that might be much more appropriate for what you end up. So that's why I focused on them in the class, and I do believe that's why kind of what we do in statistics these days. So with that, I'm going to stop here. Thank you for listening.